Okay, so we'll go ahead and get started here. Here are some examples of maybe some problems that we have gone over, maybe some of them more in depth than others. Some of this content, I just rely on you remembering this from your freshman year. Okay? So the top number, if you had 5.85 times 10 to the negative fourth, how do we change this irrational number to a whole number? So that negative 4 is telling you something. Remember, these are powers of 10. We move it to the left 4 times. Okay? So that means if we had 0.585, there's 1 time. Okay? So we need 3 more because it's to the negative 4. That means if we move it over, there's 1, 2, and 3 more times. And then if you write it like that, that's fine. Personal choice. I put a 0 in front. You don't have to do that. I just choose to put a 0 in front of that. So 0.000585 is the same as 5.85 times 10 to the negative fourth. And again, the reason that we utilize that, especially when you're dealing with Avogadro's number. Okay? Front row, are we good with this? Middle row and back row. Okay. So then this next problem, we have manganese here. And with this manganese, how many protons would manganese have? And this is how we had done these problems together in class. And it's written the same as on your paper that you have handed out that you're probably working on now, where you have a specific number written to the lower left and then to the upper right. So then we have a certain number of protons, neutrons, and electrons. So in this case, we identify the element by giving you the atomic number. So if we're looking at element 25, that's the atomic number. And what does the atomic number tell you? It tells you the number of protons. And the majority of time, it'll tell you the number of electrons, but this is a little different because this has a +3 charge to it. Okay, so what that means then, it's got 3 more of one of these subatomic particles as opposed to another. It's got 3 more protons than it does electrons. Okay, so that must mean if we have 25 positive charges, how many negative charges would we have to add up to +3? That would be 22. Okay? So we've got 22 electrons. So we have 25 positive charges, 22 negative charges. That results in 3 more positive charges than negative. And then that would be 25 and 25 if it was neutral. So then we still have to find the number of neutrons. How did we do this in class, no matter how brief we spent in time? Yes?
What do we do if it's a -3?
Okay. Well then, if this was a -3, Well, then that means we've got 3 more electrons than we do protons. Then this would be 28. You've got 3 more negative charges than you do positive charges.
Okay, so the electron is the only one that changes when you have the choice?
Correct. Because if you change this number to a 26, then you're talking about iron. Because if this number changes, then your element changes. Has to. Put that back where it belongs. Positive 3. Okay. Then we still do one more step to find the number of neutrons. 25 from 56, and that gives you, what, 31? Okay. Now sometimes, and we went over this when you were freshmen, if you had this element, and it's neutral, but calcium typically forms a positive 2 charge. We're not saying that here. We're saying this is neutral. So take this same content. This tells you your atomic number. It would be the same for any element. So how many protons does calcium have? Okay? And if it's neutral, how many negative charges does it have? 20. And then how many neutrons would it have with no charge? Okay? Sometimes all 3 of them are the same. It doesn't happen very often, but it can. Okay? So then if we're talking about the ion, if you look on your table, find element number 20, what do you see inside that box besides 40.01, besides calcium, besides Ca, besides 20? There's one more number that you see in there. I heard it, but just say it a little louder. Plus 2. Okay? It forms a plus 2 charge. So that's why we wrote that up here. So now, if we're doing these, this is for calcium now. So this has to be 20. Okay? This is still 20. Okay? But now our electrons is what? It's got 2 more positive charges than negative charges. So it would be 18. All right. Next problem. It says, if there is 7.71 times 10 to the 27th atoms of manganese 3 nitrate, convert that to grams. Okay? So I think some confusion that some of you may have. How do we know where to start in this problem? There's only one number you're given, and that's the one in scientific notation. Okay? So with that, since there's only one place to start, which is with this number, okay, we're going to have a couple conversion factors. It's either this or it could be this, Avogadro's number over moles. Okay? It could be moles over grams, or it could be grams over moles. So these are our conversion factors. Okay? So if we have 7.71 times 10 to 27th atoms, we can just put AT for atoms. And since this is written in the formula, if you want to write this out every time, that's fine. Or you can write manganese nitrate, because we know what that stands for. It's this right here, manganese nitrate. So, in order to get from atoms to grams, we have to change this to a mole first. Okay? So here's our conversion factors. Which one of these will get this number into moles? And we set it up like this. And the clue you could say is if we have atoms on top, how do we get that to cancel in our next step? Moles over atoms, or Avogadro's number. Here's your conversion factor. For every mole of manganese nitrate, we have how many atoms of manganese nitrate? Avogadro's number, 6.022 times 10 to the 23rd. Okay, so we're in moles now. That's not answering our question because it's looking for this into grams. Now we're on the home stretch. So what is our next conversion factor? We've used these. So if moles is on top, how do we get that to cancel in our next step? We need to put moles on the bottom. Moles of manganese nitrate. I suppose I did put that there. And then here's your conversion factor. Grams of manganese nitrate. So these have canceled. So then we have to have a number for this manganese nitrate. How do we come up with a figure for this? Yeah, that's where your periodic table is utilized. So manganese is 54.93, okay? 94. Okay? Okay? So one nitrogen has a weight of what? 14. And how many nitrogens are there? Okay? So 14 and 14 is 28. So 42.03. Is that right? Okay? So one oxygen atom has a mass of 16. And how many of them do we have? So you got to take 16 times 9, and that gives you, is it 144? Okay, 144. Okay, so 7.97. Okay, so then this atomic mass, again from that formula, goes here to 40.97, and we would be done once we proceed and move forward. Okay. So now, since these two numbers, not that they're on next to each other, but since they're on top, what do we do with these? Multiply, and then with this one, we divide. Okay? So, we take 7.71, okay? Second, change it to your exponent. Above the 7 key, type in 27. Take that times 240.97. That gives you 1.8578 times 10 to the 30th, but we're not done yet. We take that number, divide that by Avogadro's 6.022. Second, the key above the number 7, the E pops up, punch in 23, and then we get Or you can write that out, 3085152.28. These are the same numbers. Okay, middle row. Are we on the bus here? Back row. Front row. All right. Now, do you want to try this on your own, this molarity problem?
Sure.
All right. Is anybody looking at this and saying, I don't know what to do? Okay. I think you come up with somewhere around 14 grams. Maybe it's just under 14. Okay. So,
I got 9.
oh, maybe it's 9. All right. So let's look at this and say, all right, can we erase this other content? All right. So what we need to do then is remember there is a formula for this. Just like velocity, there is a formula for that. Acceleration, there is a formula for that. So what we want to do here is say our molarity, whatever it is, equals the number of moles of that substance divided by the volume of whatever you're trying to make here. And this is something that very similar to what some of you who are going to be future nurses are probably going to have to do, is something similar to this. You have to dilute a solution down, because how many milliliters are in a liter? There's 1,000 of them. So if you are on the nursing floor and you're looking at the doctor's orders, they're probably not going to be given that in liters, because you have to convert that down to milliliters. Okay? So with that, we know some given information here is that we want a 0.50 molar solution. So that number goes here. We would say your molarity equals 0.50, and again, that's a molarity in moles per liter. N also stands for moles. This means the exact same thing. Then, our volume. What's our volume that we want to make this solution? 250 milliliters. Now, notice this is in liters, so this is in milliliters. The numbers, it looks like it's the same, but our value or label is different. So how do we convert milliliters to liters? Do you multiply by 1,000 or divide by 1,000? You divide by 1,000. So then if we do that, it's a power of 10. You move that to the left 3 times. So 0.250 liters now. Now we're in liters. Here we're in milliliters. So our N then is our unknown, which we know is given in moles. That's what N is. Okay? So if we do what the formula tells us to do, where does this go in our equation then? Here's our equation. Where does the 0.50 go? It goes on the left side. 0.50, because that's where it says this belongs. So on the right-hand side, we have a fraction. What goes on top with our fraction? And the number of moles that we need. Because notice, okay, It's asking for how many grams, not asking for how many moles. You really can't go over into the store clause and say, I need this many moles of calcium chloride. You'd say, how many grams do you need to have to make that number of moles to go into this equation? So what goes on the bottom in this equation? Okay? So the next thing we need to do is get N all by itself. And how would we go about doing that even from physical science? Just like this, did we change the value of that? No, it still has a value of 0.50. So what's 1 times N? Just N. And if we cross multiply it here, we have to do the same thing here. So 0.250 times 0.50. 0.250 times 0.50. That gives you 0.125. N is measuring what? It's measuring moles. That is an amount of a substance. Moles of our substance, which is calcium chloride, which would be CaCl2. There is our amount of substance measured in moles, but again, we want grams. So we need to change moles to grams. And how would we go about doing that?
Yeah, we only did it where it was 1 4. Yeah, we didn't.
Oh, well, this has a -1, that's got a +2. You need to balance those out. Well, typically, just like the last problem, I wrote the compound out for you. The bell had rang, so I just quick wrote this problem up. I just did not write this for you.
So how many of them on our paper have that?
Ideally, none. I don't mean to do that. Like I said, I just thought I'd throw this up here to help you review. Okay. So how do we change this to grams now? Well, just like what we've been doing. Which one of these is our conversion factor up here? And we should throw another selection. It got erased. So we do have the correct conversion factor up there. So how do we cancel moles out in our next step? Put it on the bottom. So for every mole of calcium chloride, how many grams of calcium chloride would we get? Well, okay, for every one of these, it's 35.45. I think that's right. 0.08. Okay. Okay, so adding those two numbers together. Okay, so then what we need to do is take 0.125 times 110.98. That means we need 13.87 grams of calcium chloride dissolved in 250 milliliters would give us our 0.50 molar solution. Okay, but yes.
Can we go over how to know if chlorine has two or not? Like, do a few examples or something?
Oh, well, I should have wrote the formula for you.
Oh, okay.
Okay? But time just got away from me. So back row, are we good?
Yeah, I'm good. Yeah, good, I'm good.
Okay? Middle row and front row. All right. Okay, so there's a little over 15 minutes left. That's where we'll stop, so we'll catch up to you next time. Problem evaluation tomorrow, and then an activity for Thursday, and we'll see once that puts us. All right, we'll catch up to you next time.